Chapter 8. Canonical coordinate transformations. Previously we showed that an infinitesimal motion of an object in terms of the generalized coordinates, going from q sub 0 p sub 0 to q sub 1 p sub 1, in phase space, could be described in terms of the system Hamiltonian. The coordinate transformation induced by the Hamiltonian is canonical since its Jacobian is 1, the area-preserving property of canonical transformations. See equation 8-1. Let's now consider the general class of such canonical coordinate transformations. Let the initial coordinates be q sub a p sub a 4 equals 1 2 n. Let the transformed coordinates be q sub a p sub a, where a equals 1 2 n, and we have the transformation relations. See equation 8-2.
How general an expression can we obtain for the new coordinates, q sub a p sub a? To start, let's write Hamilton's principle from before, with subscripts suppressed. See the next equation. In terms of the Hamiltonian and the action in a modified Hamiltonian principle, with subscripts expressed. See the equation shown.
As with the Lagrangian, total time derivatives make no contribution due to the fixed endpoints. Relaxing this condition is explored later. Thus, the variation in the action can be rewritten. See equation 8-3, which gives rise to Hamilton's equations when delta S equals 0. See equation 8-4. Thus, at a guess, to retain Hamilton's equations of motion in the new variables we need to be able to express.
See equation 8-5. In reference 25, the four types of total time derivative generator functions of canonical transformations are described, with dependency on the old and new canonical variables according to q.q, q, p, p, q. p, p, the same generating function need not be used for all of the variables, giving rise to a mixed analysis much like the Ruthian analysis involves some variables being described in terms of a Lagrangian and others in terms of a Hamiltonian. Recounting the various cases is done in detail in reference 25, so won't be done here. To take a specific case, consider the transform generator function of type q.q, and let's analyze the canonical transforms it can produce, following the conventions of reference 29. Specifically, variation on.
See equation 8-6, which yields Hamilton's equation for the new variables as expected. See equation 8-7. If we now take the various partial derivatives to rewrite the total time derivative, we can arrive at consistency with the Hamiltonian equations above if. See equation 8-8.
Thus, the action description in a modified Hamiltonian principle affords a remarkable flexibility in choice of equivalent representations of the motion. The simplest thing to choose is a situation where the new coordinates are cyclic, q sub a equals 0 times a and d times p sub a equals 0. And this is what is done in Hamilton-Jacobi theory described in the next section. 8.1 The Hamiltonian-Jacobi equation. Using the derivation and notation of reference 29, there is now a simple way to arrive at what is known as Hamilton-Jacobi theory. The idea is to have a transformation such that the coordinates are cyclic. Before embarking on the canonical transformation, however, it helps to shift from function f of q sub a t to a new function, denoted S of q sub a p sub a t, by way of a Legendre transform. This new function for the condition of cyclic coordinates will be the action as denoted by S previously. So first consider the Legendre transformation, works here since all surface terms are 0 due to fixed boundary conditions. See equation 8-9.
First, the differential is by definition in terms of its dependent variables. See the next equation. But from above also have. See equation 8-10. Thus, see equation 8-11.
Where we can see that the functional dependence is indeed S of q sub a p sub a t. If we take the following relations by definition for partial derivative for. See equation 8-12. We then get. See equation 8-13.
Any S of q sub a p sub a t, given the above partials, will generate a canonical transformation by construction. Let's now choose a canonical transformation with S of q sub a p sub a t, such that h of q sub a p sub a t equals 0, since h thereby has no dependence on q sub a and p sub a. They are cyclic coordinates. in which case we arrive at see the equation shown. And since q sub a and p sub a are constants of the motion, we then get the Hamilton-Jacobi equation. See equation 8-14. This is a first-order partial differential equation that can be solved by introducing n plus 1, constants of integration, open brace c sub, a close brace a n d times s sub 0.
See the next equation. If we choose the constants open brace c sub a close brace to be the constants to set p sub a, we return to the classic form of the solution known as Hamilton's principal function. See equation 8-15. Where? See equation 8-16. The reason this form is significant is due to the latter relation. Given that the set p sub a and the set q sub a are constants of the motion, it is invertible to give a description of the motion that is only a function of time.
See the equation shown. Thus, the motion is clearly defined as a path, parameterized by t. Let's consider the derivative of s along this path. See the next equation. Thus, see equation 8-17. Or, changing the time variable notation slightly, we arrive at the form originally posited as Hamilton's action formulation, mentioned at the start of CH3.
See equation 8-18. Example 8.1. Let's start with an expression for the action. See the equation shown. What system results? What is the Hamiltonian? What are the trajectories? Solution. See the next equation, from which we can reconstruct.
See the equation shown. Thus, the Hamiltonian can be written as
see the next equation. Thus the conserved quantity, energy, is see the equation shown. This is a harmonic oscillator. Let's get the trajectories now. See the next equation. One possible set of solutions.
See the equation shown. Exercise 8.1. Find all solutions. Example 8.2. Solve the Hj equation for motion in one dimension for a particle is acted on by a force that is constant in both space and time. Solution. The Hj equation in 1D. See the next equation. A for particle in 1D, non-relativistic with force constant in space and time, have F equals negative the fraction with numerator partial differential V and denominator partial differential Q equals alpha right arrow V equals negative alpha Q. And for the kinetic energy we have the usual.
T equals 1/2 mq dot squared period. The Lagrangian is thus, L equals T minus V equals 1/2 mq dot squared plus alpha Q period. Now to construct the Hamiltonian, first the momentum. See the equation shown. Thus, see the next equation. Using this in the 1D Hj equation, we get.
See the equation shown. If we guess a solution of the form, see the next equation. Solving for the function w of qe. See the equation shown. Thus,
see the next equation. Exercise 8.2. Solve the Hj equation for motion in one dimension for a particle is acted on by a force that is constant in space and increasing linearly in time.